So, hello everyone. My name is Chris Murphy. I am a senior tech artist at Epic on the DevRel team. I'm going to preface this with a little bit of an apology. Getting hit with jet lag, something fierce right now. So, the worst thing you can do with jet lag, I think, is then go do a bunch of math. Do you think you're here for VFX? No. No. It's just math. So this is going to be a live build, because I'm not a smart man. We're going to be building things, but I really want to be clear on what today's session is in all of its roboto glory. Today's session is not going to be building a really cool explosion. It's not going to be building a really cool anything, actually. But what it is going to be doing is showing you a bunch of things that make a difference. And I'm going to do a little bit on nanite tessellation, and displacement. But honestly, the bulk of this is going to be looking at some other concepts. I'm going to be looking at simulation stages. I'm going to be looking at particle readers. I'm going to be looking at grid collections. And I'm going to be looking at neighbor grids and data channels. And the funny thing with all of those topics is they're really, really useful for artists. But they also really sound like they were named by engineers. And the problem with that is when you hear these things, you're like, oh, data channels, why would that be useful? Why would a grid collection be useful? So today is going to be a bunch of simple demos. Of me building stuff, explaining how these concepts work. I'm trying to make it as digestible as I can, because ultimately, when I see people using Niagara, 99 times out of 100, they're still using Niagara like Cascade++. You know what I mean? Like for any of the newcomers, Cascade is UE3's and early UE4's particle system. But they're still kind of using it in the same way. And there's a lot you can do in Niagara that's just drastically removed from that. But awkwardly, folks just kind of don't know about those things. So let's go make some video game stuff. OK, so what I'm going to do is I'm going to start with grid collections. And the reason I want to start with grid collections is, grid collections and sim stages, is I think these are one of the things that is it's a little of a gateway to advanced Niagara usage. I think it's a good place to start. I'm going to go ahead and I'm going to spin up a new Niagara emitter that's going to be a fountain. And I'm just going to call this like NS fountain. OK? Nothing too fancy about this. But what I want to do is I want this to have particle collisions with the world that are going to be a little bit different. I want to get this, and I want to have a big old plane underneath it, whereby anytime those particles touch that plane, I want to leave a mark. So I kind of want to paint onto it. So we're going to be spraying particles in the air that whenever they touch the surface, I want to leave a mark there, right? And, And to do that, what I'm going to do is I'm going to go ahead, and I know that if I want to paint onto anything, I probably need a render target. So I'm going to start with that and just call this RT underscore impact paint. Cool. And I'm just going to drop that straight on. I know, I broke the rules. I put the texture straight on it. OK, so we're going to be painting impacts from this fountain into here. Here's where we begin. So with this system, we have a basic fountain, nothing fancy about it. But what I want to start with is over here. You've got an emitter spawn, which calculates what happens when something spawns in the emitter. Update is as the emitter is updating, it's the logic it processes. Particle spawn is the logic that the particle does when it's created. And then you have particle update, which iterates over all of the particles while it's running. I'm assuming everyone pretty much knows this at this point, right? But if I click, first off, turn this into a GPU emitter. But if I go stage, add stage, this creates what's called a simulation stage. And a simulation stage is a really fancy way of saying we're adding another update loop. So after it's run that update loop the first time, it's going to run another update loop that goes through everything again. Now, by default, that runs through all the particles again, but we can actually run that update loop over anything we want. So think of it this way. If I was to say, hey, when this emitter is created, I want to spin up a new variable, and that is going to be a grid 2D collection that I'm going to give the name my grid, or gritted, apparently. Hang on, let me just fix that up. I warned you all about the jet lag. All right, so we've got my grid. Now, a grid collection is essentially a 2D array that just holds whatever information I want to put in it. So it's storing it on an x-axis and a y-axis, okay? And that information, if you think about it, what I'm actually going to do is my grid collection is going to represent this render target. Just imagine that you were laying like an Excel spreadsheet over the top of that thing, and every time one of those cells was being calculated, it was like, how close am I to the nearest particle? And based on its proximity to the particle, it'll paint a color to be like, am I being hit or not hit? So I've created a grid collection. While I'm here, I'm also going to create a particle attribute reader, which I'm going to call my reader. I like giving them the word my, personally, just because I can really explicitly see that it's the thing that I created and not something auto-generated. Weird habit. So I've got my grid and my reader. Now, a particle attribute reader is a way for any system, including itself, to analyze particle information inside of that system. So if I have a reader, I can actually have something else analyze where all of these particles are and then chase those particles, for instance. Or in this collection, my grid is going to read the particle information to find out information about it and know what it wants to do with its life. So I'm going to give this a name just for, I'm going to call this like render to grid. And I'm going to go ahead and add a function to it. Okay, and I'm going to add a scratch pad. And I'm going to call this draw to grid. All right, so within here, this is the logic we're going to process for every single cell as we iterate through it. And to show you what that looks like, I'm going to get a reference to the grid. And just as an example, I'm going to get execution index to unit. I know I'm going quickly, but oh, I've got so much ground to cover. So here's how this works. You'll see this phrase thrown around a lot, to unit. Anytime you have a grid, be it 2D or 3D, to unit means show me what the grid coordinates are between 0 and 1. So if I have a grid that is 512 by 512, then 0, 0 is a value of 0. 512, 512 is a value of 1. You know what I mean? It's kind of normalizing the grid. And the reason I'm doing that is because this will let me kind of like draw the UVs. I'm just going to draw the length of the UVs or something here. And I'm going to output that as a value that I call distance. Now the next little thing I'm going to quickly mention here is that anytime you have an output value that is stack context, it means that if you use it in a particle, it will save it as particle.distance. Anytime you use an emitter, it'll be emitter.distance. But when you use it in a grid, it will now actually save this variable to the grid as like the grid's information.distance. Cool. So that's plugged in. We're not quite where we need to be yet, because there's one other thing I need to do, which is after I spawn the grid, I need to set the resolution. Now, I typed in set resolution, and we saw nothing. And the reason for that is most of the grid behavior is not in the library, but rather when I turn off the library, we have a ton more grid stuff that we can use. So I'm going to get that. I'm going to set the resolution of my grid. You'll notice at this point that a lot of what I'm doing is a little bit boilerplate, unfortunately. So we have a 512 by 512 grid, and I'm just going to preview that on there. Now, it's still not working, and the reason it's still not working is this last little bit, which is before I said that this is a separate update loop that iterates over whatever we want it to, I need to actually tell it what we're doing. Right now, it's iterating over all the particles, but I'm going to say I want you to iterate over my grid. Now, it's OK. The biggest mistake, easiest mistake, most frequent mistake, I should say, is anytime you create a scratch pad, you've got to remember to bind your variables to the things that you created inputs for. But interestingly, that's now got a black to red value. Do you see that? Because as the unit is moving further away, the length is getting further. So I kind of just drew a little spot. That's nothing impressive. But what is good about that is that we now know that we can render information to a render target. And we know that that information can be used, right? So now that I know the grid collection is there, I'm going to do some quick math. And I'm actually going to remove you. What I'm going to do is I'm going to really quickly do some math to just calculate the position of where this render target is. 0 to 1, 0 is the top left corner, 1 is the bottom right corner, right, on the UVs. However, we're offset because the pivot point is in the middle. So you don't need to know how to do this bit. I'm just going to gloss through it. But if I subtract 0.5, it's going to offset the circle to the center. If I multiply it by, I think I scaled the thing up by 4. So if I multiply it by 400, that should now give me negative 200 to 200 in my local space. Again, you don't need to know how to do this bit, but I need it to show it to you. That's now going to give me a vector 2D, which is like the xy coordinates. And I need to have x, y, and z. Sorry, no, yeah, x, y, and z. Z. So I'm just going to really quickly, you can do that to me. If I can position. There we go. All right, we got there in the end. Sorry, so I'm just doing this real quick because what I want to do is convert that from two-dimensional to a position in space, and then I want to find where that is in the world, which means I'm going to transform it from local to world. Again, this is really quick. And the next thing that I'm going to do is going to be far more interesting. I'm going to bind this to a value that I'll call like cell position. OK, so here's the next bit. What I need to do next is I now need to look at this position, which is I now know where it is in space, right? But I need to look at that position and compare it to a particle location. And this is where a lot of people are like, well, I guess I need HLSL. Because I need to iterate over every particle and find out where they are, right? And then calculate it. Cool little thing you can do is not use HLSL, which is if I was to get like the particle reader. Sorry, I'm not used to this keyboard and it is messing me up. There we go. If I was to get a particle reader, normally what people think they need to do is write custom HLSL. And as a heads up, you can write your own blocks of code here. Cool thing is you can actually right-click on any interface, and I can like click that and then paste in the function names and stuff like that if you don't know what the HLSL functions are. But I also kind of hate writing stuff in HLSL. I think I'm just well and truly on the node train at this point. So what I would actually suggest doing instead, if you're someone like me, is we have a thing called a map4. And the map4 is great because everyone tells me it doesn't exist. What it is a for loop. You can run for loops in Niagara, except they're backwards. So how a for loop works in Niagara is it starts here, and then it rolls back to the last time you had a map set. So the last time you set variables, it just cycles between those things, if you get what I mean. So that kind of controls the space of a for loop. Anyway, I need to run this for every particle. So I'm going to find out the number of particles. And now for every particle that's there, I'm going to go ahead and access that cell position that we got. And I'm going to access the position of the current particle that we're examining. Now, this literally lets you look at any attribute that is stored in that particle, like the particle reader, any particle information. So I can look at the position of the there we go, of the current particle. And in theory, what we have on screen is that will give me the information of the first particle, the second particle, the third particle, the fourth, fifth, sixth. And I can just do a normalized distance. You're here somewhere, I'm going to find you. Range. Sweet. All right. So this function looks from this location to this location. And if they're more than 100 centimeters apart, because it's set to 100 here, sorry, Unreal units, what it will do is it'll be a value of 0. If it's within that, it'll become white. I'll show you what I mean. If I go this value and just plug that in, I'll call that distance again because I kind of like that. And I change the namespace to here. what that should do, once I remember that thing that I said everyone screws up, you've got to plug it in. All right, see that little red dot that's bouncing around now? That's because every one of these is saving over the previous particle, right? Like I'm not grabbing the highest value that it's been. That's okay. I'm literally just going to say, hey, look at the value that's there. But this time, let's access the current distance value that we've got. Sorry, I know this is getting a little bit cluttered. I'm like, yay, nodes, and then I show you a mess. But I swear it's normally a little bit better when I'm not standing in front of 500 people. Okay, good. All right, just go to the max value, ship it. Oh, apply. Okay, you will always get this error. If you ever try and access a value that you've never given a value to, it's going to panic. It's okay. Just literally click the value and be like, it's okay to be 0. All right, cool. So that is now saving all of those positions as they kind of stream out, right? What I'm going to do, just to make this a little bit cleaner, is I'm not just going to access the particle position. I might as well also access the sprite size. Oh, I hit the wrong one. There we go. Vector 2D. Yeah, cool. Sprite size. Now, sprite size is just a 2D vector that gets stored in every sprite. And if I get the length of that, and I make that the distance, that should now be the same size as the particle. Yeah, cool. So now that that's done, save. I'm just going to do one last little thing, which is simple, which is I'm going to create a user parameter that is going to be my render target texture, RT output, seems good. And that's my impact paint that we created just before, right? And with that in, my grid, render output to that. Cool. So now anywhere they're hitting, they're now kind of saving that information off. You get what I mean? Now, I wanted to show you this. I know it's not super fancy, but I wanted to show you this because I really want people to start understanding that like we can handle collections of data, we can process particles in a different way. And now this is a gateway, right? Because if we think about what this could be, I'm going to skip some stuff and come back in a second. Oh, eye adaptation. So see these clouds out here? These clouds are actually a Niagara system that's painting. This here is the output, where it's a circle that's gradually moving around, painting clouds into the world. Do you know what I mean? Like, you can grab your Niagara outputs and feed them into all sorts of other data and make some really interesting effects. I can have them feeding clouds, but I could also have them working on more advanced effects. So really quickly, like if I was to come over to here, so nanite displacement is a feature that we added in 5.5, right? Well, we added it in 5.3 and didn't really tell anyone, but it's stable in 5.5-ish. So what's going to happen here is nanite displacement allows you to have these like offsets of values, right? So in this situation, if I was to look at this material that we've got the bumps going on, nanite tessellation, all that's going on here is I'm reading in a displacement value onto an offset, which is kind of giving me this. If you want to get this working on your material, you just need to make sure that enable tessellation is set up. And if you want to control how far out it goes, you do that by setting the magnitude value in here. Honestly, it's pretty straightforward. Amusingly enough, the biggest gotcha involved is you need to make sure static lighting is disabled if you're doing it on skeletal meshes, which will cause a crash in 5.5 preview 1. It's fixed in main. It should be fixed in 5.5 preview 2. But on static meshes, it should work out of the box. So I bring this up because nanite displacement, sorry, my eye adaptation is gross. There we go. Yeah, cool. Isn't that nicer? All right. I bring it up because you can use a texture mask for a nanite displacement to start doing things like this snow, okay? Which is cool. But I wanted to make sure that people were aware of another really useful thing, which is if I look at this material, I have a mask. This texture object here is called Mesh Paint Texture Object. Mesh Paint Texture Object is honestly probably the coolest feature we added in 5.5 in my opinion, like for all of the other cool stuff, and it sounds so dull. I accidentally had two of them in the same space. All right, here's what it does. If I go Mesh Paint, and I click on this, actually I'm gonna go I'm going to remove everything. So by default, this is what you're going to see. But when I go texture color, add, I'm going to crash. All right. That's pretty funny. All right, I'm going to try that one last time, and if it doesn't, I'll move on from that. Real shame, because it was definitely working non-stop. All right, so mesh paint modes, texture color, that's OK. I'm going to go with the one that I've already added to it. But I will fix this eye adaptation again, because it's just hurting me. OK, cool. Mesh paint mode allows you to paint straight onto the mesh. Shift-click, left-click. And it will actually save. This is something you couldn't do with Nanite meshes historically. So you can have like a statue in there and comfortably have like 30 different differences between different assets that look, they're still using the same mesh, but you can bring in like inherent variation. It's really something folks need to get on. Usually you click add and then you paint. The remove button did not work for me just then, so we'll all back away slowly. But there's no difference between what I'm doing there and running my particle system. Like I know I'm projecting them up into the air like a fountain, but like conceptually speaking, this here is able to now paint onto a surface, right? This could be a mesh. And I bring this up because if we know that we can paint that kind of mesh displacement and fun stuff through render targets in Niagara, we can couple these things together. This is where tech artists and VFX artists truly shine, is like how do we like get these two things together and make them stick together. So we've got weather simulations as an example of things that we can do, but what I'd love to do next is I want to spin up a new, sorry, I've lost my content folder when we crashed. I'm going to dupe that and call it ns_character example. Yeah. Cool, so character example is going to be something similar, except this time around I'm going to get a friend of mine called Quinn. And what I want to show you is this. So I've got Quinn, and I'm going to use her as the thing that I'm painting onto. I'm going to grab a Niagara system, spin that up, and I'm going to throw that in. What did I call it? I called it character or something. Yeah. All right, cool. All right, so we've got this character in there. The next thing I'm going to do, just really quickly as we kind of get this set up, is I'm going to spin up another render target. You can dynamically create render targets from Niagara. You don't need to create bespoke ones, by the way. So don't stress about that. But I'm just doing it so you can kind of see this setup a little bit clearer. All right, my character example is still my fountain. I'm going to change the user parameter for my texture output. That's weird. OK, it looks like when it crashed, we lost my user output values. That's fine. I don't think we lost anything else in the process. I guess we'll find out, huh? Cool. Sorry about that. I'm just trying to catch up from where we were in the crash. Threw me a little bit. All right, so I'm going to output to this character texture mask instead this time. And I'm going to make sure you're correctly plugged in. So I can see that's working. It's saving to my texture. What I'm going to do instead, sorry, Quinn. What I'm going to do instead is I'm going to get this material and apply it to there, and apply it to there. And I'm going to change one thing. Ahead of time, I changed Quinn to have an extra set of UVs. I set her UVs up to be UV1. Okay? So what that means is the material that got auto-generated here needs to preview on UV1. So I did that so that she had like unique UVs instead of any mirroring or anything like that going on the character. But what I'm going to do instead is over here, I'm going to spin up a new user parameter that is a skeletal mesh reference, and I'm going to call it my mesh. Cool, so my mesh is going to be there, and in my draw to grid, what if I just ignore everything I did here, but instead we access the skeletal mesh, and we say, hey, this here is a UV. Remember, we did 0 to 1, basically, in the grid. We iterated through it. Conceptually speaking, like, there's no difference between getting that and like finding out which triangle is at the current UV index that I'm looking at. And this will actually tell me where on the character it is. And if I know where on the character it is, I can then take the next logical step, which is I can look up the triangle data in world space. And this will tell me the exact position of that current UV that we could be painting to on the character. Cool. So why that's good is this, so you're in. All right, cool. So I need to do one other little change. It's still painting, but now it's getting a bit weird. The reason for that is whenever you bring in a mesh like this, you need to make sure that it knows which UV sample it's referencing, which in this case needs to be reference 1. So reset that. Good. Okay, give me 1 sec here. Ah, I'm like, why is this not referencing? It's because I did the thing that I said everyone screws up, and then I just demonstrated that to you again and again and again. All right, so that actually is working. I'm going to shrink the particle size down so it's a little bit, let's go to 10 just a minute. Let's also maybe, we've got a sphere shape location already. Feeling like if we put this above her head, slightly forward, you can ignore this part. I just want to create some vague sense of snow or something. Get rid of the add velocity. Yeah, reset. Well, messed something up. Did I double type a value without realizing it? Direct sets. Gonna go back to you. All right, sure, why not? Oh, that's why. I did it as a position offset instead of a, and none of you told me. Yeah, good. All right, so that is actually working. You can see as those particles are kind of falling through, they're painting the surface of the character now. And if I was to shrink this down to have little small particles, that should be a little bit more evident. All right, and obviously I would want to normally destroy these, and I might actually want to iterate over the previous frame, so I did kind of like a paint between the two locations, which is why we're seeing that circles. You can do that later. What I care more about right now is if I was to do this, but I wanted to have like 5,000 particles, this gets out of hand really quickly, and not just because like she's now being showered by snow particles, but it gets out of hand really quickly because if we're doing 512 by 512 and then we're multiplying that against every particle, you're going to have a bad time, right? Especially like as this number increases, as the life of the particles increases. And that's why the next thing that I want to do for the next, I got just enough time, this will work. Next thing I want to do is neighbor grids. So neighbor grids are a really interesting thing that we added that are super useful that no one really knows about. Let me tell you. How it works is we can create a grid around the player or the emitter that is three-dimensional. And what happens is in every single grid cell, they store one thing. What they store is which particles are also in that grid cell. Does that make sense? So we have a whole bigger, like a whole three-dimensional structure which says this is which particles are near me. Okay, again and again and again. And you're probably like, why does that matter? And that matters because right now I'm iterating through every particle, right? But if each UV cell was able to say, which grid cell am I in? I'm in this one. Cool. Which particles are also in that grid cell? Then it means each grid cell only needs to iterate through the particles that are nearby. You know what I mean? Like we've created a local check for these things instead of checking every particle. Yeah, great. So I bring that up because grids, again, like you hear the word neighbor grid and it just doesn't sound like a good time. But if we create one of these, which I'm going to have there, I'm going to call it like, it hurts me to write neighbor without a U, just for the record. So I'm going to create a neighbor grid. The biggest trick is that the neighbor grid needs to have some kind of attributes set for it. So first off, we're going to set the library only, strikes again. Huh. Sorry, folks. I really should have had more coffee. Neighbor grid 3D, set resolution. Which grid? Whatever I called it. Actually, I called my neighbor. Oh, that's going to come back for me. All right. We can set this up however we want. Like you set up how many cells you want. So I'm going to be like, hey, look, we want like, I can reliably say there's probably not going to be more than 30 particles per cell. And you want your cells to generally be big enough to encapsulate an entire particle. So I'm going to just pick a number out of thin air and say 30. Why not 30, 30? Okay, cool. So with that in, we now need to have the extent. The extent is going to be like, well, how big is the grid? I'm just going to eyeball it here and say 200 by 200 by 200, which gives me a 2 meter, 2 meter, 2 meter. In fact, it's good to push that off to a user variable, so it's something that we can tinker with later. So in theory, that gives me a hypothetical grid construct. Now, that grid has no place in space. It's like it's the concept of a grid and the data storage for a grid that could exist, but it has no like way to figure out where something is within it. And that's where a really common function that we use a lot here, which is units to world transform. What this does is it literally says, based on this offset, which is my simulation's position, and based on this rotation, which is going to be my simulation's rotation, and these extents, which will be the things I just pushed off to a variable, that is how I will define this grid. You know, if something says how big is the grid, this is what says that. All right, I know this is in-depth, meaty stuff, and you're expecting explosions. My apologies, but it's every YouTube video out there shows you how to do cool explosions and things like that. I really wanted to focus on like the parts of Niagara that people just don't know about. I want to push people further where I can, right? So we've got that. We can see the grid. I wanted to skip 5 minutes of this presentation, so I added something to the engine, which is pretty useful, which is this neighbor grid 3D visualize function. I'm just going to make this function. I'm going to call it visualize grid. And this needs to know how to define the unit to world, which is auto-created by that function from before. It needs to know which grid we're iterating over, which I called my neighbor and didn't add the word grid in, and I've regretted twice and used it twice. Now, that is already working. It's painting the bounds of the grid around the character. Do you see that? So that's where the cells will be. What's really cool about this function is if I go to particle update and I say populate neighbor grid, which needs to know unit to world, and again, neighbor, spelt wrong, that should, oh, and last but not least, iterate over the grid data interface. Cool, save. I hate that that's probably it. Nope. Sorry, folks. Give me just 1 sec. First off, I'll visualize empty cells. Yep, that's working. We are populating the grid. We're setting the resolution. We're iterating through it. That's all getting put into there. Neighbor grid position is reading. Position 90s is reading. Let me just verify it's not that. 5 points for whoever can pick what I've screwed up. Unit to world, unit to world. Simulation to grid unit. Oh, yeah, good. Sorry, I translated it from one space to the other incorrectly. But what that's actually doing now is that is actually forming a little grid cell around, around each of these, which is adding it, which is nice. There's actually, I realize I've actually made another mistake, but that's fine. So that's actually putting every cell, it's figuring out which grid cell everything's in. Do you see that? So like those little grid cells that are green are the ones that have data in them, yeah? Little mistake that I just made is this function, there's a better one, and that is actually called fill grid 3D neighbor. Sorry, that's why I was thrown before. I'm like, why is this looking weird? And the difference between the two is that added everything to one grid cell, right? But this one does this. Now, what's interesting with this is actually finding the surrounding neighbor cells. And the reason that's more useful is because that way if I'm in this grid cell, but I'm overlapping these ones a little bit, it's still querying that. So it's actually giving it more information that they may need to query, but it's more reliable because you don't get like weird transition of grid cell issues, right? Anyway, last little bit that I want to have there is with this in play, my draw to grid function, if I wanted this to use grid cell information instead, there's a bit of legwork here. I'm going to do it, and then I've got 5 minutes to do data channels, which will be fine. I'm not busy, you're busy. Okay. So I'm going to access my neighbor grid, and I'm going to find out where my neighbor grid is. So I want to get the, all right, this is a bit of logic to step through, and hopefully you can look at the YouTube video later to work this out. But I'm going to get the current position of the data cell that we're looking at, and I'm going to do a matrix transform, which is definitely one of those things that sounds cooler than it is. I'm going to transform that position into my grid logic, where it represents 0 to 1. To do that, I need to read in a matrix, put on my favorite sunglasses, and I'm going to call this world to units. Again, I don't really expect people to go home and just immediately smash this out, but I do think in a perfect world, some of these strangely named things in Niagara make a little bit more sense to you. And that's the starting point for some of these things. So I've got index, and I'm going to cache off the index to a linear. Now, all that means is this is figuring out what cell it's in, like X, Y, and Z. Linear is kind of like, imagine all of those rows were stuck one after the other and stored in like a big single line. Sometimes you need to look things up through a linear index. Sometimes you need them through an X, Y, Z. It's just how it be. But I'm going to grab this linear, push you off to here, and I'm just going to call current linear. All right, whatever, linear. Okay, sorry, we're running out of time, so I'm like, okay, cool. So with that in mind, we're almost there. I now no longer want to iterate through every particle. Instead, I want to get the grid, and I want to get my neighbor grid. Whew. And I want to get particle neighbor count. So that's saying how many neighbors exist inside of this grid cell. I actually want to get the smallest number between either the neighbor count or the max number of things you can fit in the cell. Weird quirk of neighbor grids is, you know, before I said no more than 30 cells per, no more than 30 particles per cell. It will actually keep counting once it goes over 30. So you need to tell it, you know, chill out, just give me the ones that I asked for because we don't want to mess that up. But in technical terms. Cool, that should now iterate through every particle in the cell. And the last bit that I need is, and this is again a little bit of legwork, but I care more about this conceptually, is now that I have this grid, I want to access yep, this one, cool. This takes an X, Y, and Z, and then the neighbor index. It then tells you what that is inside of the particle reader. Basically, this transforms all of that data to be like, this is the particle that you're after right now. And what that means is if I was to access that linear value again, need coffee. And I was to go linear to index. Again, a little bit janky. X, Y, Z. And this was the current iteration. All of that together didn't really get us very far. In fact, we're going to see the same visual result, right? But this is the difference between someone on YouTube saying, yeah, but that won't run on your computer, versus, yeah, well, sorry, do I sound bitter? For the record, actually, I'd like to get this out there. Every demo I've put together in the last quite a long while was done on my laptop. And every time, without fail, someone on YouTube says it requires a beast computer. And I've been like, oh, no. All right, world to unit. Great, great, great. Cool. I'm missing a value somewhere, which is why we're getting that clip. Oh, sorry, wrong function. Actually going to turn off the visualization. Sorry, folks, I've missed one value somewhere. Get particle neighbor, iterate through, calculate linear. Linear is getting the particle counts. That's stepping through. What am I missing? It's giving me the same picture every time, which means it's giving me the same grid cell every time. If it's giving me the same grid cell every time, then what we're looking at is probably screwed up here. All right, I'm going to solve this in either 1 minute or not solve it and move on to the next topic. We're very close though, so I'm really suffering here. Position of vector, world to unit, min. Sorry about this, folks. Get the particle neighbor count, get the max per cell. Everything seems fine. What am I doing wrong? It's grabbing the interaction, but it's painting the wrong particle. Well, that's embarrassing.
Is it getting to the neighbor grid part? It looks like it's stuck in the cell and not like getting the next cell.
You got it, you got it, you got it, you got it. Yeah. I think what you've done is, yeah, I'm iterating. When I changed this, I think oh no, nope, take it back, don't got it.
Keeping it.
You should keep it. All right, look, I'm running out of time, so I will jump to the next bit. Damn, I do have a working version of this that I'll throw up on the dev community later. This was me just crawling particles over her as necessary, and I can put as many of them in there now. With a grid setup, you can push it up to like, I've had 5,000, 6,000, and it's been fine, which is really cool, because you're able to kind of like split this out and just massively work this out. But I want to point out that when you're using this kind of logic, there are some really good examples that hopefully inside of the Niagara content examples make a bit more sense. Like the particle reader is being used here with sim stages so that these particles stick to one another, find the nearest one, create a structure, and then that structure is then used to like split them apart. So you've got this like cool kinds of setups. But there's some really, really good Niagara setups that you can go through in the content examples, but no one really knows how to understand them. Like they're too complex to really get the foundations, which is why I wanted to step through grids. I wanted to step through neighbor grids, and I wanted to step through sim stages so you could start to understand what you're looking at in that demo room. Last little thing I want to do with my remaining 7 minutes and 20 seconds, here we go, is data channels. So I created this scene, and I present you a problem. Actually, it's great, but the problem is this. If I have a game where I'm spraying bullets at a wall, and we're getting like impact effects coming off of it, right? Often I would be spawning a new impact effect for every impact on the wall. You're all still with me? Cool. The problem with that is if the front row joined me in and we were all shooting bullets that said wall, really quickly we have just a gross number of impact effects that are going to be spawning, right? Problem. So what we actually have is a cool system that no one knows about, but if you spin up a data channel, just going to type it in here. And I'm just going to call this impact example data channel. And I'm also going to go ahead and get the impact effects we were just looking at, that like pew pew. Copy here. And I'm going to rename this to be like impact data channel. this system is now going to be leveraging that. So here's how this works. Inside of the blueprint for this ship, instead of the ship creating a system at that location, we're going to do something different. Actually, I'm going to set up the data channel first. My apologies. So a data channel is a way of kind of pushing off a whole bunch of data and then accessing all of that data in Niagara. So I'm going to create a data channel island setup, and I'm going to add some variables to it. Position, which is going to be of type position. And we're running out of time, so I'm just going to do rotation, which is going to be a quaternion. Don't worry, it'll auto-convert. Now, the other thing that I'm going to do here is align static is fine. What this actually does as a system is Unreal says, in this case, 5,000 by 5,000 by 5,000, but fuzzier. What's going on with that screen? It will actually say, is this emitter playing within a 5,000 unit square? Yes. If so, grab the effect that's coming in and stuff it into the existing emitter. Does that make sense? So all of the ones that happen together in that single area can get batched together, which is really useful. So if I come back here, I can be like, all right, so I want to have that. I'll set that up as align static. I'm actually going to turn on the debug as well so you can see it. But in my turret actor, instead of creating a system in the way that you would expect to, I create a data channel impact where I read in the position and I read in the rotation. Told you to auto-convert. Right, so that's now going to be the position of the effect and the rotation. I'm also going to do a search parameter. Search parameter is like how do they get batched? And you can batch them by component, which is cool, or you can just batch them by location. I'm going to do location so that they all kind of get put into an island together. Now, if I was to close this, I haven't set anything up yet, so this is all still wrong, but if I was to close this, with those debug values on, we can actually see that these are the islands of where those effects would have been spawning in. So this would be spawning 2 emitters. I didn't show you before, but it was spawning 230 effects or so because I'm deliberately firing a whole lot of bullets. In my data channel, I'm going to tell it that what I want this thing to do is to spawn this system, which is right in front of me. System. Sorry, folks. Right there. System. Sorry. Like I said, coffee. Data channel. Great. All right. I'm going to do this as quick as I can just because we're 3 minutes out from time. My data channel system looks like this. First off, I need this system to now run infinitely. However, I want to complete it if no effect has been spawned in the last 5 seconds. Okay? In this system, I'm going to tell it that I want it to be based on the I want the emitter state to just do whatever the system is doing. I get rid of spawn burst instantaneous. And instead, in my emitter spawn, I'm going to have a new scratch. Oh, that was a funny story. Sorry, folks. I want to have a new variable. New variable. I just did it twice. New or existing parameter, which is going to be a data channel reader. By the way, you can write to data channels from Niagara, which is cool. I'm going to have this reader, and what it's going to do is instead of spawning the way that we usually do, I'm going to actually create the scratch pad that I really wanted this time, and I'm going to call this like spawn from data channel. It's going to have a reader as an input, which is basically going to get that, and it's going to spawn conditional. So it's kind of going to be looking at that system, finding out what it needs to be creating, and spawning that many particles, which in this case, there's just a little bit of boilerplate. Hey, is there a session immediately after this, or do we go to lunch? All right, you're stuck with me for 2 extra minutes. Sorry, am I threatening you with a good time? All right, so that's in min spawn, max spawn. That's all I really need to do here, okay? And then over here, where I'm initializing the particle, I'm going to, instead of setting the position here, I'm going to create a scratch pad that I'm going to call like initialize from data channel. I'm going to capitalize that C or we're living in anarchy. That's going to be a data channel. And I need to access the spawn data. There we go. And then I need to read. And if I select the one that we've got there, that now feeds me the position and the rotation information. Do you see that? And I can just pump that information straight into the particles that we're about to create, right? So I can set particles.position to be this position. The rotation, I'm just going to push off to here, and I'm going to call it like spawn direction, I guess. Apply. We go back to here, and I make sure that everything's actually set up with my data channel, because I apparently learned my lesson. 50 to 200, I guess. Still getting a failed here. What's failing? That's fine. Initialize some data channel, compile error. Sorry, folks. Just seeing what my log is. This is going to be. Oh, yeah. Sorry. I didn't read in the emitter ID. It would help if you plugged it in. And this is the execution index. All right. Video games. Okay, cool. So that's theoretically fine. Just because of paranoia, I'm also going to set some bounds so this thing definitely renders where it should. Might be fine, but I have trust issues now. I feel like I let you all down on that previous effect. I don't know what I did wrong, but I didn't have time to check it, you know? Cool. In theory, that's fine, though. Yeah, sick. So that's doing the same thing. Before, that would have been 200 and something effects, except now, if I go stat Niagara, we're sitting at 30. And I bring that up because another cool aspect of this is this stuff can all be made from within Niagara as well. So you can actually have data channel information spawning from other places and feeding in effect data. If you look at things like our volumetric effects, so when we're doing fluids and stuff like that, instead of creating 100 fluids, which is really intensive, you could use a data channel to inject all of those fluids into a single fluid emitter that's in the correct region. Do you get where I'm coming from here? See why this is really valuable, but again, it's just kind of one of those things that's both really valuable, but just really not well known. So my apologies for running a little bit over time. Hopefully this session has been useful for you. It's been a little bit erratic, and God, I need some coffee. But thank you all very much for your time. If you have questions, I'll be floating around for the rest of the event.